Hello, my name is Gabriel Vielma, alongside Hollis Alden and Wesley Bush, and we are Latrine.
My name is Wesley Bush, and I acted as the lead programming/engineer role on this project.
My name is Hollis Alden. I acted as the team manager on this project.
My name is Gabriel Vielma, and I acted as the lead design. As for our problem, most common toilets use more water than necessary while flushing, and that can cost us money in the long run. Latrine is a device made to save water consumption on toilet flushes. The majority of toilets are outdated and use more water than necessary. Current solutions are mechanical, expensive, and require an involved installation process. Latrine looks to fill a void in the toilet space by providing a budget-friendly and easy-to-install solution. This is an example of our competition. This is a very efficient toilet that uses 1 gallons per flush. It's for $137, and that might not include installation process. And then this is our prototype, which is $80 and can fit into any toilet.
So the way Lean Latrine actually works is that the microcontroller utilizes a water pressure sensor to check the water level. When the water level is at an appropriate point, the water pressure sensor notifies the microcontroller, and the microcontroller tells the servo to hold up the float valve, which stops water from coming into the toilet tank. When it flushes, the water level goes down, and the servo releases the float valve until the microcontroller notifies it to start the raise the arm once more. So our initial design was to reconstruct the inner workings of a toilet to prevent common problems such as flooding or water running, while also using less water than current systems. We controlled how much water was used through an app. While in our final design, we weren't able to get the flooding or water running addressed, we were able to get the water consumption addressed and create an app that can control this device. So here we have the major components. The ESP32 with Wi-Fi and Bluetooth is just the microcontroller that tells all the devices what to do. There we have the 12 kilogram torque servo. The ESP32 terminal is where the ESP32 sits, and all the wires go into it to control the other devices. And this is just a picture of the pressure sensor without the tube by itself.
Some challenges we faced during the duration of this project included a lack of documentation for the servos that we were using, which resulted in a lot of trial and error to figure out how exactly to control those servos through code. A few components breaking, including a couple servos and a pressure sensor, due to a soldering mistake, which we remedied with the very fast shipping times of Amazon Prime. The servo mount, which we were initially planning on being the side of the toilet with the rest of the components, using a long lever, but we eventually figured that we could use a component that was already in the toilet. We could mount it on top of that. And of course, COVID-19 and the distance between us. Since I'm in Austin and the rest of the team is in San Antonio, scheduling and meeting online became a little bit of a challenge. Some future plans we have for this project include knowing more accurately how much water is being used in the toilet, so that we can report maybe a liter estimate of how much water the user is saving, instead of having them change just the water level that they want the toilet to get to. We could have a prettier encapsulation. We could fix some more common problems with toilets, including, say, when the flapper gets stuck open, causes the toilet to never stop flushing, or if the flapper is leaking, or we could have a detection system for knowing when the toilet is overflowing, and then we could add additional app functionality. The product, before it is able to function, has to first be calibrated. So through the app, we'll start the calibration using the calibration. And what this process does is it tells the app where top level of the toilet is and the bottom level of the toilet is in terms of pressure. And of course, pressure will be different in different areas of the country. In higher elevations, it will be less. In lower elevations, it'll be more. So this process is necessary to determine, also for different toilet sizes, where this level is. So the level of the toilet is actually not accurately represented. before the calibration is completed, but it's the bar graph on the right side. And when we finish the calibration, you'll see that whenever we flush the toilet again, it is accurately showing where the water level is. So it's going down rapidly right now. And then in a moment, it will turn around and begin increasing again. And then sometime later, it is still increasing. It increases slowly because the water level increases slowly. But you can see that it has increased the maximum level. And the float valve, although it's not very visible in this video, it has stopped. So the calibration is successful and it accurately shows the level of the toilet. So we now get to show the fruits of our labor here by setting a desired water level on the app using the left bar graph. And then when you flush the toilet, you see that the level goes all the way down on the right side. And if we skip to where the toilet is almost finished filling to that desired level, we can concentrate on the servo up there where the mouse is circulating, and you see it just activated because the levels are now the same.
As for commercialization, we came up with a basic marketing strategy. We will create a video ad, post it on Facebook with vague targeting. Then based on people that engaged on the video or visited our website or added to cart, we can put them into another group and retarget that audience. And this is an example of the vague targeting we would start with. We did a age range from 30 years old to 50 with the interest of home improvement, technology, and gadgets. And our initial reach will be 42 million people, which is a good amount of people to start with. Thanks for watching, and now we will answer any questions.